whiteboard so I don't forget. I will do it. Well, see, but I can't really do attendance if Lauren's not here. I mean, I can, but. Somebody asked me something.
For the notes and with the problem that you put like made a video for,
Yes.
Is that like there's no place to take notes on that? Is that just like
no, you should take your own notes. Okay. That's what I thought about that. I'm like, I really should, and then I thought, you know, they can write it down themselves, and you should want to. Did I at least write the problem down for you?
No.
Oh, all right. Sorry about that. All right, so Guess is sleeping, one can only assume. And Lauren and I had several emails and we're supposed to meet at several different junctures of the day. There she is. Now I can do attendance. All right, so that's that. Yes, we did recently spray that, so go ahead and wipe it off. All right, so we're gonna really start talking about chapter 4 today, and talk about displacement, velocity, and acceleration vectors. So the main things that I want you to understand or remember is that everything that we did in one dimension, all of the equations, all of the ideas, all of the, this is how we solve a problem, all of those things translate into 2 and 3 dimensions. Okay, so you can't say, I've never seen this before, oh my God, what am I gonna do? You've seen this before, okay? You know how to handle this. And so all of the vector quantities that we've been using, we use X for position, V for velocity, all of those things can be expressed in 2 or 3 dimensions using unit vector notation. And last week, which seems like a lifetime ago, we talked about unit vector notation, right? I, J, and K. It was in the video and we reviewed it. All right. So, and the final thing to remember is that the motion in different directions along different axes is considered independent. So the gravitational acceleration that you feel in the Y direction isn't going to affect the motion in the X direction. Okay. There are situations kind of in the second half of this class, which you are not taking with me, where something, some force, some interaction in one direction can cause a change of motion in another direction. But we will not be dealing with that. Okay, so if you go on and take the next semester when you're in college next year or in 2 years, that can happen. But right now, for what we're going to study, those 2 directions are separate and they do not affect each other. Okay. And I think that was it. So I wanted to try a couple of problems. So you should have like class notes for today, right? That have a couple of problems listed in there, yes? Okay. So the first one is kind of what I would call plug and chug, but I still think it's important to kind of see it. All right. So we have, so this is example 1. Or example first or whatever, okay? And it said an ion's position is initially, so I'm gonna call that Ri or R1. I think I call it R1, my own notes. Okay, is initially 5.0 I minus 6.0 J plus 2.0 K. And 10 seconds later, it is at what I'm going to call R2, which is negative 2.0 I plus 8.0 J minus 2.0 K. And all of those numbers are in meters. Lauren. I tried to put everything together, but I tried to make, yeah, it says class time, displacement, velocity, and acceleration vectors. Oh, I didn't distribute it? Okay. but I really thought I went through and like shot out everything over the weekend. Okay.
Yeah, I'll try.
Okay. Sorry about that. I tried, but there was this really cute puppy that kept sleeping on my lap and things just got. Mira? I have no idea who that is. No, it's not like Mira Reagan. Mira Reagan spells her name differently, now that you say that. But it's pronounced the same way. So that's her name. It's a video game character that my boys could agree on. The other options were Maya and Willow. I still like Willow, so I call her Maya or Mira Willow Bixby. But I believe, and maybe Lauren, I'll put you on the spot, but I think Mira is light in Hebrew. Okay, well, you don't have to, but I had some colleagues in grad school and they named their daughter Mira, and I thought that was the explanation, but that kid is probably like graduated from college by now, so it's a long time ago. But anyway, it's you have Mira variable stars in astronomy, so I feel like at least there is some connection that goes beyond it. But that's my sweet. We finally slept through the night, as I said earlier this morning. So, what is the average velocity during that 10 seconds? So we'll say over here that delta t is 10 seconds. Okay. So what do we do when we solve a problem? What's the first thing we do? Not necessarily graph, but what? It's going to look like a graph, but picture. We're going to draw a picture. Okay. So you got to draw axes in 3 dimensions. Yes. Oh, I have 3 axes up there. I have 3 axes up there. What's going to freak you out is that this is X, this is Y, and that's Z. So X is coming out of the board. It has to be this way for a reason that will become apparent in a couple months. No, you just have to accept it. Most of the time, I am more than happy to let you make your own decisions, but there are a few things that we do for a reason, and it has to do with vector multiplication, and it is the convention. It is the accepted way of doing it. Now, when we do things in 2 dimensions, which is where we will do most of what we do, then you can let X be horizontal and Y be vertical, and everybody's happy and nobody cares. But if you're going to do 3 dimensions, they have to look like this. Okay, it's just the way it has to be. Okay. So X comes out of the board. That is the important thing. So I am going to try to plot this. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 5, 6. 1, 2, 1, 2. All right. So R1 is going to be plus 5 in X, minus 6 in J, plus 2 in K. So my position vectors here go from the origin to whatever that X, Y, and Z coordinate is. Okay. That's what a position vector does. It measures the distance or indicates the distance from the origin, wherever that is, to the point. Okay. So that's going to be my R1. My R2 is negative 2X, positive 8J, negative 2K. So it's going to be down there somewhere. Okay. So if I'm going to find the average, what is the definition of the average? Lauren. Okay, so let's start by reminding ourselves it's going to be the displacement over the change in time, okay, which, as Lauren correctly said, is going to be R2 minus R1 over whatever that change in time is, because at t equals 0, I am at R1, and at 10 seconds later, I am at R2, okay? And so after last week, you know how to subtract vectors, right? Because subtracting vectors, R2 minus R1 is really R2 or plus negative R1, right? And what's negative R1? I flip all the signs, so it's pointing in the opposite direction, and then I add them together. So I could do that graphically, right? I love it how you're all nodding your heads. It's a pain in the butt. You're never going to be able to do it and be accurate about it. I bet you we all drew very different actual diagrams for R1 and R2, okay? Because it's difficult to draw 3 dimensions on a 2-dimensional screen, okay? So this is really not going to be the most effective or accurate way of doing this, right? So the whole point here is that R1 and R2 are in unit vectors. And we know that the only thing that can change, I'm sorry, how do I want to put it? That only things in the same dimension, the same X, Y, or Z direction can affect each other. So we can treat each of those separately, okay? So I can write the average another way. I can say that the average, which is equal to basically delta R over delta T, okay? I can break that down and make it delta X over delta T times I plus delta Y over delta T times J plus delta Z over delta T times K. Okay. And then I just need to look at what the change in dimension is, or what the change in value is for each dimension separately. So I can further make this x2 minus x1 over delta t, where x2 is the x component of R2, and x1 is the x component of R1. And do the same thing for the other dimensions. Okay, this is going to be much easier. And if you did this, you would not have to write out all these steps, but we're doing it as an example. We're doing it as notes. So I just want you to see what everything is. Okay, so what's my x2 value? Tia. Well, it's not, I don't need the I anymore, but negative 2.0, good. And what's my x1 value? What? 5.0, okay. We know they're meters. And what's my T? 10, right? So these are meters, these are going to be seconds, that's times I. Sophie, what's my Y2? Okay. Eva, what's my Y1? Okay, so minus negative 6. Again, my delta T is seconds, And the units for all of those R values are meters. Annabelle, what's my Z2 value? Okay. Dagny, what's my Z1 value? Okay, again, over 10 seconds. Meters, that's going to be my K hat direction. Okay. So what do we get? What's our I component going to be? Do not get out your calculator or use the one on your laptop. Okay, negative 0.7 meters per second I. Lauren? Nope, because I have to divide by 10. It's okay. Nope, did the whole thing right there to get my velocity. About my J component. 1.4 meters per second J. And how about my K component? Negative 0.4 meters per second. Okay, because it's negative 2 minus 2. Okay. All right. Wait till everybody writes this down, and then I got a thing or two to say. So let's think about this for a minute. Okay, so my velocity in the X direction is negative. Okay, and if I look back at my picture, my particle starts over here in the plus X and it ends over here in negative X, right? So it would make sense that that X velocity points in the negative direction because I'm moving from a positive value to a negative value. Okay, if you think about the Y components, we're starting at a negative Y and ending at a positive Y. What sign do you think the Y component of the average velocity should have? Positive, which it does. Okay. And then if we look at the Z direction, we're going from a positive Z direction to a negative Z direction. So again, our average velocity should point negative, which it does. Okay. So how do you find the magnitude of this average velocity? Great. Okay. So basically what Fiona said is we're gonna square all the components, add them together, and take the square root. It's just like you would do if you had 2 dimensions, you'd use the Pythagorean theorem, right? Your magnitude or your resultant would be C. So C squared would equal A squared plus B squared. So one of the great things about all the dimensions of space is no matter how many dimensions I have, I can just keep adding terms. Okay. So this is going to be the square root of negative 0.7. That should probably be 0 meters per second squared. It's 1.4 meters per second squared plus negative 0.40 meters per second squared. Okay. So what do we get? 1.6 what?
1.6. Oh, meters per second.
Okay. Let's see what other people got. Annabelle agrees. Tia agrees. Fiona agrees. Dagny agrees. Eva, you get it? Okay, we're waiting for Sophie. All right, everybody got the same answer. Okay, so this was really just kind of a let's play and look at what happens in 3 dimensions. And it's also to hopefully impress upon you how important it is to look at unit vectors, okay? That once we get into 3 dimensions, it is really not helpful to be drawing pictures and trying to calculate things with rulers and scale drawings and stuff, okay? All right, so I would like to do one more problem. I think we have time. Yeah, I think we got it. I got 22 minutes. So this comes from your online textbook, number 28, but I think I wrote it in the OneNote document anyway. Yes? Yep, it is The Boat Leaves the Dock. So Annabelle, why don't you read it for us? Mm-hmm. How did I write this? Holy cow. Oh, I did. I did. That's the problem. Something went wacky. No, it doesn't repeat. I don't know why it repeats. It was the cutting and pasting. All right, let me at least fix this one and then we'll do it. Okay. Because I tried to cut and paste it from your book so I wouldn't have to type it all out, but apparently that was a mistake anyway. Okay, so the boat accelerates in the plus I direction due to its motor. Okay, that's going to be the acceleration of 2.0 meters per second squared I, right? But in addition to that, the wind gives that constant motion in X and Y that we have to take into account. So what we're going to do is figure out what the motion is going to be in terms of the motor. And then we're going to add to it the velocity of the wind. Okay. Make sense? Okay. So the first thing that we're going to do is look at or consider motor, or the motor's contribution. Now remember that I can consider X and Y separately, okay? So if you've started watching some of the videos that I made for, I think I asked you to watch them for tomorrow, one of the things that we do is we make a separate list of knowns for X and Y. Okay. And then remember that as always, we have the same variables. We've got X and X0. We have V0X, Vx. We have AX, and we have T. And then we have a whole separate set of knowns for Y. We have Y0, we have Y, we have V0Y, we have Vy, we have AY, and we have T. Okay. So remember as well that T is the only variable that's the same for both lists. Okay, either the object is moving, either it's in the air, or it's not. It's not going to move for longer in X than it does in Y. Okay. So we can plug in some things that we know. And remember that we're only dealing with the motor. Okay. So we're going to say that object starts at the origin because it's got to start somewhere. So we will let the dock be the origin. Okay. And if we're only considering the motor and what the motor does, then the boat actually starts from rest. Okay, and we're going to add in what happens with the water later. Okay. And then what kind of acceleration does the motor supply? Okay, in what direction? Okay, so positive 2 meters per second. And it doesn't put any acceleration in the Y direction, right? No, that's a very good question. Sophie wants to know if we have to include the acceleration due to gravity, and we don't because it's moving basically at all the same height. It's not falling. This XY grid is a grid that I've put on the ground. Okay, so it could be like north and east. Okay. All right. And what else do we know? What else can I add here? Time, right? And how long is the boat moving for? Okay, 1 second. And like I said, time is going to be the same for both. And then we need to make our find statement. And what are we supposed to find? Okay, so we're supposed to find the velocity. But remember, I expressed that velocity as Vxi plus Vyj. So I can really figure out what Vx and Vy are separately and then just put them back into this equation. Okay. So let's start with Vx. If I want to find Vx, which equation am I going to use? Dagny. Sounds good to me. Okay. We know that V0x is 0, right? Because it's starting from rest. So that means Vx is equal to axt. And then we just substitute in. So ax is 2.0 meters per second squared times 10 seconds. And again, we don't need our calculators. $20. Does anybody know why I keep putting that dot after 10 and 20? Sig figs. Okay, good. No. On a test, I will make sure it is abundantly clear or you ask. And on the AP exam, it probably means there's 2 sig figs, but in general, you can't make that assumption. It's a good question. And I'm surprised I didn't catch it when I was typing this up because I tried. Okay, I meant to. It's a phantom decimal point in the write-up of the problem, which obviously had other problems, as we all know. All right, so I got to find Vy too. What formula do I use for that? Yeah, same one, right? V0y plus ayt. But V0y is 0, ay is 0. So what's the velocity that I'm getting from the motor? 0. Okay. All right, we good? Okay, so here's my boat. Okay, I am getting at 10 seconds. I have 20 meters per second that's coming from the motor. But the wind is also giving me some velocity, right? So the wind is giving me velocity in the x direction of how much? Okay, so v wind x is 2 meters per second. And what other direction is the wind blowing in? Okay, so we'll let y be this way. So this is v wind y, and that's what? 1 meter per second. My scale is very far off here. Okay. And recall that I can add together vectors of the same type. So these are all velocity vectors, which means I can add them together. And then I can also add together vectors by their components. So that if what I really want to know is the velocity of the boat, which is going to be equal to whatever velocity the motor has given the boat, plus the velocity of the wind, that I can add things together by components. Okay, so for the motor, I have 20 meters per second I. And for the wind, I have 2.0 meters per second I plus 1.0 meters per second J. So I add together my I components or my X components, and that's going to give me 22 meters per second I. And I add together my J components, so that's going to give me 1.0 meters per second J. Okay, we good? All right, so what does part B ask us? Okay, so we want to find the X and the Y, knowing that this is our velocity. Okay, so I probably need to make my knowns just a little bit, well, do I? How did I do it here? Oh, I see how I did it. Okay, so we can again break this down into two parts. We can break down the contribution from the motor, okay, and we can break down the contribution from the wind. All right, so if we look back at our knowns here, and what's Y going to be for the motor contribution? 0, it's not going to be anything, okay? How do I figure out what X is from the motor? If I want to find X, what equation am I going to use? Yep. X equals x0 plus v0 xt plus a 1/2 ax t squared. Okay. And we're pretty lucky. X0 is 0, V0x is 0, so that whole term goes away. And I just have 1/2 AX t squared. So AX is 2.02. Times 10 seconds squared. Again, you do not need your calculator. How far do we go under the power of the motor? 100 meters. How many sig figs does that 100 meters have? 2. Okay, so I could write it as 1.0 times 10 squared meters, and then it would be abundantly clear that I have 2 sig figs. Okay. Okay, everybody got what they need? All right, so I know that X from the motor is that 100 meters. It's an intermediate answer, so I'm going to keep that extra digit around. What's Y from the motor going to be? 0. Okay. And then I've also got to figure out X from the wind and Y from the wind. Okay. So how do I figure out Y wind? What equation can I use? I'd rather you not. Just use V times T, because then you're going to use it sometime when you shouldn't use V times T. Where that comes from is Y0 plus V0 YT plus 1/2 AY T squared. But we know that we start from 0 and we know that there's no acceleration. So it gets you to Vy times T, but it gets you there in a better way, along a better path. Annabelle. Nope, I'm going to add Y wind and Y motor together to get my final Y. Lauren. This is for the wind. So the wind has a constant Vy the whole time. So V0 is equal to Vy because it's not changing, it's not accelerating. Okay, so what is the velocity of the wind in the Y direction? 1. Yep, 1.0 meters per second. It's going to blow for 10 seconds. So that gives me 10 meters in Y. Say that again. Yes, yes, yes. Okay. And then I can use the same formula to find X wind. X0 plus V0 XT plus 1/2 AXT squared. Remember again, though, that I'm not really starting from anywhere. I'm just kind of looking for the difference, and the wind is not accelerating. So X wind is x wind is going to give us v0 x times t. And what's the velocity of the wind in the x direction? 2.0 meters per second times 10 seconds, not 10 meters. There we go. So what's that going to give me? 20 meters, 20 point meters, right? 2.0 times 10. Okay, so that's going to be 20 meters. So I add together my x's, I add together my y's, and I can say that at t equals 10 seconds, I'm going to be at 120 meters in x, 10 meters in y. I might write that as 1.2 times 10 to the 2 meters and 1.0 times 10 to the 1 meters. Getting a little picky, but just to keep our sig figs right, okay? Second. Because I'm just looking at how far it moves in that 10 seconds. I'm just looking for a difference. I'm not looking for the whole, I'm just looking for the difference. So it's kind of arbitrary where I started. I'm going to take the difference anyway, so I might as well let it be 0.
That's the second point is just rewrote it, right?
Yes.
Okay.
Yes, I just rewrote it. The second line is they're equal. I just rewrote it, and so it was clear how many sig figs there were. Okay. So we all right? Okay. We will go over the test after everybody has taken it. Guess has not taken it yet. Although you can see, I guess you can see your grades. You can see your comments. Okay. One more thing before you go. Go back. Come on. Go back. This is actually what I want to bring your attention to. Please note the difference between my Z's and my 2's. There is a reason why my Z's are crossed. There is a reason why my T's have little hooks on the end so they don't look like plus signs. Okay, just pointing things out. All right, have a great day. I'll see most of you tomorrow morning for calc.
Golf on the red bus. Golf on the red bus.
Have a lovely evening.
I got your email.
Yeah, hang on, just let me stop this up, finish this up.